What's going on, everyone? So today we're going to learn about average velocity. Let me just start saying or telling you why we need to learn about average velocity. With this one, it's going to help us when we have situations of great complexity. That looks like a V. Of great complexity. Or as the guy from OpenStack says, complicated trips. I like this one better. So that's why we need average velocity. It's going to help us with complicated trips. And what is a complicated trip? What is a situation of great complexity? Well, we have an example problem. As you can see, it's very lengthy, and that's why it's a complicated trip, okay? So now, next, I would like to write down the equation, the formula for average velocity. Some textbooks write average velocity as V bar. This is what this line represents, V bar. Normally, I would write VAVG for velocity average, although you want the V to be bigger. And that is delta x divided by delta t. And you might be thinking, oh, this is just like the one we looked at in class. Yes and no. We use that because we described velocity as a rate of change. But we said that since our starting position or starting point was the starting time was 0, we just had delta x divided by t, okay? And for this one, we do have to take into account the time interval. It's very important. So then let me talk about what delta x and delta t are, the meaning for average velocity. Well, delta x is, as we stated, a change in position, or we can also call it displacement. Sometimes I'm going to say displacement, sometimes I'm going to say change in position, depending on my mood. I'm kidding, depending on the nature of the problem or example. And delta t is a time interval. Let's try this again, at least the R and the V. Maybe that's better. And let's keep this fraction look for consistency, okay? And this is the one I want you to write down, like the final one, right? So V average is equal to delta x divided by delta t, which is the same as x minus x naught divided by, let's try that one again, t minus t naught. We could say that it's final minus initial, final position minus initial position. But I don't like to teach it this way because sometimes you're going to have different displacements, meaning you can divide your problem in different parts, 3, 4, 5, maybe 6 parts. So if you had different displacements or different distances that you walked, or this person traveled, whatever, let's say if you divide your problem in 4 parts, you would have 4 different positions, so x4 minus x naught. If you had 6, x6 minus x naught. If you had 3, x3 minus x naught, okay? Same with the time. So let's box this one so you don't forget to write it down. Okay, there you go. Okay, and then just as a reminder, the units are meter per second because displacement, we measure in meters and time in seconds. So now let's look at the problem so that this makes more sense, okay? It's a long one, and I'm going to read it. It is what it is. Daisy sets out from her house or home to deliver flyers for her smoothie business, traveling due east along her street lined with houses. At 0.5 kilometers in 9 minutes later, she runs out of flyers and has to retrace her steps back to her house. That would be west, right? Because she was going east to get more flyers. This takes an additional 9 minutes. After picking up more flyers, she sets out again on the same path, back again along east, continuing where she left off and ends up 1.0 kilometers from her house. This third leg of her trip takes 15 minutes. At this point, she turns back toward her house, heading west after 1.7 kilometers and 25 minutes. She stops to rest. What is Daisy's average velocity? Answer in meters per second. Okay. So the first thing we need to do is, or my suggestion would be, let's make a table, okay, with the different times and positions. Normally, I would make the table and then use the table as points to draw my graph, just like you would do with y and x. Well, this would be x and y, right? Because time is independent. X and y. But I'm not going to do that. It's right here. I have it. But normally, I would get the points and then draw the motion graph, position versus time. Okay. And we have different displacements or intervals, right? So here, 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 so it's 4. Now we have 5 boxes because we have to account for time 0 and 0 position, or x time t naught and x naught. So let's start with those. We know that t naught would be 0 here, right? 0 minutes and 0 kilometers. So x naught 0. I don't have to write the units because my table states that this is minutes and this is kilometers. Okay, very good. This is T naught. Now the first one, so let's use highlighter, would be from here to here, right? So at this point, this is T1. So at T1, as per the problem, the time was 9 minutes. And after 9 minutes, Daisy was at 0.5 kilometers from her house. So x1, 0.5. Next, let's use green from here to here. So the next point would be here. This is T2. At time 2, now if you write 9, that's incorrect, even though it says 9 minutes, right? But it says additional 9 minutes. So we have to add 9 plus 9. That's 18 minutes. And this is interesting. At time 2, x position is back at 0 because she went back to her house. Now let's go for the third one. Yeah, I guess. Let's see if I can find kind of like, yeah, I guess this is good. So from here to here, and then I'm going to pick red for my color. This would be time 3. So time 3, it took 15 more minutes. So we have 15 plus 18. That would be 33. And x3 would be at 1 kilometer from her house. So 1. Okay. And the last one, I'm going to pick, yeah, like this very light purple. Can't even see it, but that's fine. Here. And this would be T4. And then T4 had 25, additional 25. So it's 25 plus 33. So that'd be 58 minutes. And now this is very important, okay? Some students would want to say, oh yeah, so x4 is at 1.75, but that's incorrect because check it out. From starting at T3, right? This is a starting point, like for this line. So from here to this line, the time axis, this is 1 kilometer, right? However, when we write down our point is the 1 minus 1.75 because she went 1.75 towards her house, but she was 1 kilometer away from her house. So we only take into account this negative part. And then you can even see it here, right? So the displacement, the position would be negative 0.75. Let me make sure this fits. I want my table to look nicer. So x4, negative 0.75. Right? Because this is the 1 kilometer plus the 0.75 going in the negative direction. Don't forget, negative for this one just means direction. Okay? So now we have all of this. How do we find the average velocity? Well, then what I like to do after I have my graph is, let me use blue. Oh no, different color. I guess purple it is. When we find the average velocity, guys, for the entire trip, right? We're going to find the average velocity for the entire trip. What we're finding is the velocity, the average velocity from here to here. This is the average velocity for the entire trip. This line, the average. So before even I do my math and get my equation, I already know that my answer is going to be negative because this is a negative slope. Don't forget that when we have position time graph, a slope means velocity. If it's a positive slope, positive velocity. Negative slope, negative velocity. This is what I'm finding, okay? And then if we use the equation for slope, we can just get the points here minus, use the points here and the initial points, right? Like ordered pairs or coordinate, and find the average velocity. Now, that's for the entire trip. If they asked you find the average velocity from T0 to T3, well, it would be this line over here. Now, if they asked find the average velocity from T0 to T2, it would be 0, right? Because look, she went back to where she started. But we're going to talk about that later or a bit more next class. For now, let's focus on this one, right? So we know we're going to have a negative slope for sure. Let's follow our equation. So then the average is equal to, you know what, let me do it here so that I have enough space. The average is equal to delta x divided by delta t. Oh, let me just state that is for the entire trip. So average velocity for the entire trip. It's very important that we state, okay? This one. Let's move this. You know what? Let's move this one. And we can assume it's the entire trip because they're not given as an interval like T1 to T3 or whatever, or at 30 minutes, 40 minutes. So you're going to assume it's the entire trip. So delta x would be x4 minus x naught divided by T4 minus T naught. And this will be negative 0.75 kilometers, don't forget the units, minus 0 kilometers divided by times 4 is 58 minutes minus 0 minute. And the reason why we cannot just not include t naught is sometimes they're going to ask you what is the average velocity from time 1 to time 4. Then you would find this, right? Or from time 3 or time 2. Now for this is our first example. That's why I have the entire trip, okay? And once we do the math, the average is, so negative 0.75 minus 0 is negative 0.75 kilometers divided by 58 minus 0, so 58 minutes. And of course, we're going to have a negative number, just like we wanted. That's going to give us a negative velocity, negative slope. So that is negative 0.75 divided by 58. Negative 0.013, right? Going to round up. So then our average velocity equals negative 0.013 kilometers per minute. Now that's our first answer, and it makes sense, right? Negative slope, negative velocity, perfect. Now the last step is just convert it into meters per second. Don't forget, we write down what we want, and then we write what we have. So we have negative 0.013 kilometers. And so let me just start with the t-chart now rather than later. Here you go. And we have 1 minute, right? That's our ratio or rate. Kilometers per minute. This number of kilometers per 1 minute. I need to cancel kilometers. I know 1 kilometer has 1,000 meters. That's why you have the prefix kilo. That's why when you have more than 1,000 followers on Instagram, it says 1K, 2K, etc. And then kilometers cancel. Meters is what we want. So we need to make sure we highlight, right, so we know we're done with it. And then now we continue with the minutes. We need seconds. So we're going to cancel minute with minute. 1 minute is equal to 60 seconds. Minute cancels minute, and we have meter per second. And the math is pretty simple. That'll be negative 0.13 times 1,000 meters. I'm not going to include this times 1. You know it's going to be the same. Divided by, oh, let's try it again. 1 times 1 is 1, so I'm just going to say 60 seconds. And so is this, let's just do the 0.13, right? So negative 0.13 times 1,000 divided by 60. So negative 2.17 meters per second. Negative 2.17 meters per second. So our final answer would be V average is negative 2.17 meters per second. We box it. And that's it. This is average velocity for complicated trips.